So in this video, we're going to talk about what's called the kinetic theory. And I was looking over these slides before I started recording and came to the conclusion that they're perhaps a bit overly technical with a little more information than is strictly required here. So I'm going to do my best to kind of summarize the information here. So essentially, what kinetic theory attempts to do is to describe the energy in a material due to the movement of its molecules. So imagine we've got a box here, and inside that box we've got all these little atoms, and they're just pinging around, bouncing off all sides of the box, just bouncing. So these are like the atoms inside a theoretical box, and every time they collide off the sides of that box, they're exerting a force on it, like a little collision, like a tennis ball bouncing off of a wall. And so essentially what we have here is a derivation of a formula. The force is equal to the change in momentum over the change in time. And then through some various substitutions and simplifications, we eventually get to this equation here. So this is the force equals mass over length times n is the total number of molecules, times the average velocity squared over 3. And then if we look then and keep going a little farther, pressure is just equal to force divided by area. So now we introduce area into that formula. And again, through some rearrangement and simplification, we get here to this point where PV equals 2/3 N times 1/2 mv squared. And then again, with a little bit more substitution, we finally get to this. This is really the punchline. This is what all of that derivation was leading up to. The kinetic energy of the molecules is equal to 1/2 mv squared. Or, I mean, that's nothing new. Kinetic energy is 1/2 mv squared. We knew that. Or 3/2 kT. So that's essentially how we can translate kinetic energy from 1/2 mv squared, which we knew, into this new format, 3/2 kT. Okay, so what is K? K, we actually introduced earlier. K is that Boltzmann constant. Is it with 2 N's maybe? I think it might be. The Boltzmann constant. And T is the temperature. So essentially what we can see from this is if the temperature goes up, then the kinetic energy goes up. And if the temperature goes down, the kinetic energy goes down, which we'd kind of already talked about. Like if you have a gas at a relatively low temperature, the molecules are going to be relatively close together and not moving very much. But if we heat it up, they're going to spread out and they're going to start moving around a lot faster. So in other words, they have more kinetic energy. The kinetic energy goes up when the temperature goes up. So we can describe the amount of kinetic energy within the molecules of a gas right here, 3/2 kT. Okay, so I just went back to confirm here. Boltzmann is spelled with 2 N's, and the Boltzmann constant, K, is equal to, why is that not working? Pen's not working. Let me fix that real quick. Okay, there we go. K, the Boltzmann constant, is equal to 1.38 times 10 to the negative 23rd joules per Kelvin. So note the units here. That means that the temperature you use in here, T, must be in Kelvin. Okay, so make sure you're using the correct units. So the kinetic energy of a gas is 3/2 kT, where K is a constant, the Boltzmann's constant, and the temperature is in Kelvin. So we can continue with this idea to find the velocity, the average velocity of molecules if we know the temperature. And so what this is root mean square velocity. RMS stands for root mean square. And why do we do that? Why do we need to find the root mean square? Essentially what that means is we're squaring the velocity and then we're taking the square root of it. Why would we do that? We're just doing one mathematical operation and then undoing it to get back to the original. Well, the reason is because, remember, velocity is a vector. And so these gas molecules are going off in every direction, okay, all over the place. And so you might have some that have a positive velocity and others that have a negative velocity. And we just want them all to be positive. We just want to know the magnitude of the velocity, the absolute value of the velocity. So we can do that by squaring it, which makes it positive. If you take a negative velocity and square it, it becomes positive. And then when we take the square root, although that might technically be a plus or minus, we usually infer from a square root that we mean the positive root. So that's the reason we do that. We take the root mean square just to essentially get everything positive. And that root mean square is equal to the square root of 3kT over m. So again, the K, that's Boltzmann's. And, excuse me, the T must be in Kelvin. Don't forget that. This slide is really all it's showing is sort of a bell curve representing the average speed of the molecules. So you've got some molecules way out here that are super fast. You've got some down here that are really slow. And in the middle we've got the average. And there's more of them that tend to shift over towards the high side. So the root mean square velocity is not at the peak of the bell curve, but is actually shifted over here to the right. So the amount of kinetic energy in a substance affects its temperature, and vice versa. Higher temperature gases have more kinetic energy, but if you put more kinetic energy into something, it will get hotter. It will, its temperature will rise. Another thing it will do is it can change phase. So if we have a gas and we take away kinetic energy from it, if we reduce its temperature, eventually that gas will liquefy. So this chart here shows critical temperatures at which you can apply a pressure. If you apply enough pressure, you can liquefy a gas by applying pressure to it rather than dropping its temperature, so long as the critical temperature is less than that. So in other words, for water, if you keep the temperature below 647 Kelvin, you can liquefy the gas by applying pressure. And so there are these charts available, these diagrams, they're called phase diagrams. And what you see here in the green area, this is where the material would be solid. So if we're talking about water, we're talking about ice. And liquid, it's water. And here it's vapor. So of course if you increase the temperature, of water, you're more likely to cause it to turn into a gas or turn into vapor. if you're let's say at a pretty low pressure here, and then if you reduce that temperature, you're going to cross over this line into the solid region. So you can actually at very low pressures jump right from a vapor to a solid. Now up here we would go from gas to liquid to solid. So like along here, from here to here to here, just by reducing the temperature. And then you can look in the vertical direction, theoretically, if we have vapor here and we increase the pressure on it, we can liquefy it by adding pressure. And so where all three of these lines meet is called the triple point. And I've got a video embedded in my PowerPoint that's posted on Blackboard. I try to post it separately as a video that actually shows liquid at its triple point. Well, I say liquid, but it's predominantly liquid, but then it begins to like boil and turn into vapor, and then it cools and goes back into a solid, and it keeps cycling between these three phases. If you get the pressure and the temperature just right, so that you're right at that triple point, all three phases of matter can exist at once, and it's pretty cool to see. Okay, so let's say for a moment we have an open container of water in a hot room. What's going to happen is the molecules of water with the most amount of energy are going to get some energy from the room, and they're going to have just enough energy to go from that liquid to a gas phase. And that's evaporation. So there are some high energy molecules along the surface that are just short of having enough energy to be a gas. And if the room is hot and they absorb a little bit of that energy, they will finally have enough to jump out of the water essentially and become a gas. That's called evaporation. So if the hottest molecules up here with the most amount of energy are leaving, what they're leaving behind has an average lower temperature. So that's evaporative cooling. That's why people sweat, if you've ever wondered. The sweat on your skin evaporates, leaving behind a cooler sweat liquid on your skin, and that makes your body feel cooler. The opposite process is called condensation, when there's vapor in the air that is just barely has enough energy, and some of that energy then goes into the room, leaving behind a molecule that no longer has enough energy to remain a gas. It drops back down into a liquid. Not always conveniently inside the container. Oftentimes condensation occurs on the outside of the container, right? If you've got a nice cold beverage in your hand on a hot summer day, the outside of the glass will sweat or develop this condensation. Now, if we were to close off the system as we have shown here, we put a lid on it so the vapor can't escape, eventually this headspace of the container becomes saturated. So an equilibrium is occurring at that point, where the amount of molecules that have enough energy to become gas do, and they become trapped in that area, and so we have saturated vapor just above the surface.